Hello and welcome to this video on pressure in gases, lesson 16 of the Particles and Energy Scheme. And as anyone who has ever worked with me will know, this is one of my favourite lessons to teach because it's a really nice opportunity to get students thinking and making the kind of deductions from our particle model that scientific thinking is all about. So the way I like to introduce this is just with some really simple concrete examples. And what you'll see in the slides is that the structure of the lesson is really just looking at concrete examples that illustrate what we call the gas laws. So that is the relationship between the number of particles and the pressure in a gas, the relationship between the temperature of the gas and the pressure of the gas, and the relationship between the volume of gas and its pressure. And the key idea that I want to get across here to students is that really pressure in gases is not that complicated. It's quite simple. It just depends on particles bouncing into the walls and pushing outwards. That's it. Now we do need to give them some language. We need to prepare them to be able to talk about this in a very precise way. But the fundamental idea here, and it comes back to our guess, our particle model, that if matter is made up of these tiny particles all zipping around all over the place, then you'd expect them to push out. And everything that we can deduce from that model turns out to be true when you carry out experiments. So the example that I like to start with is with a balloon. So I tend to draw a balloon like this, and I say this is kind of a deflated balloon. Looks a little bit like that. And what I ask students to do, coming back to that idea that we've repeatedly referred to throughout this scheme of work, is to say science tells us about things that we can see in the world in terms of these models that we can't see. So I zoom in on this thing that we can see. We've done lots of zooming in already. I zoom in on here. I say, well, if you were to look inside this balloon, which is deflated at the moment, what you would see is the particles in a gas. But there wouldn't be all that many of them. I'm just going to draw 5 like this. And again, this is just an opportunity, as always, with all of these lessons, to just build on that prior knowledge. So we know that they move randomly in a range of directions and at a range of speeds. We can build on this idea that temperature is just a measure of the average speed or the average kinetic energy of those particles. So what I've got is some particles zipping around like this. Now what I want to explain to students is that if they were inside a box like this, what happens to the particles is that they bounce off the walls. So what's going to happen here with this one is it's going to collide and bounce off the wall like this. This one is going to bounce off the wall like that. This one is going to bounce off the wall like this. And all I'm going to show to students is, because as these particles move around randomly inside their container, they exert an outwards force on the walls. So I'm going to draw a little arrow like this to show that these particles, because there's not all that many of them, they're given a little push outwards like this. Now you might want to add some keywords here. You might want to add the word force. Sometimes I even color code it like that, which is fine. Depending on the group that you've got, if you think actually when they come to write about this later, they don't need these keywords, you might want to leave that out. But I'm going to put force here for now. And at some point we're going to need to talk about the word collisions. That's something that they should be aware of by now, but what we need to emphasize in this lesson is it's all to do with the frequency of collisions, or how often. And that concept of frequencies, it could well be something new to students. So what I want to do is then ask students to consider, well, what happens if we blow air into the balloon? So it's quite nice to actually demo this, just so they really relate that concrete change, you blowing air into the balloon, with what happens in terms of the particles. But hopefully what they would recognise is this balloon is going to then be inflated. And again, that's another piece of vocabulary you might need to teach them. Inflated. And all that we do in this part is just zoom in on the inflated balloon like this. And then I would ask my students to consider what's going to be different about this picture after I've blown a load of air into the balloon. And what you want to elicit from your students is the fact that the difference between this picture and this picture is that in here there's going to be way more particles. So I'm just going to draw lots and lots of particles inside here like this. And again, they're randomly arranged. They move at a range of speeds in different directions. So I'm just going to draw a few like this. It's a good idea when you're doing this to try and get kind of an equal number bouncing off each wall, just to make the diagram a bit neater. So I'm going to draw a few going like this, and then let's have a few going up here like that. So what I've got here is lots and lots of different particles all zipping all over the place, and there's lots more of them this time. So then what I'm going to explain to students is that, well, here you're going to have way more collisions every second than you did in the first example. So just at one instant, like we're looking at here, that one might bounce off there, this is going to bounce off here, and so on. I'm just going to show that there's way more collisions in this first example than there was in the in the second example than there was in the first. And again, because that might be a new concept, this idea of frequent, you might want to add, and you could even do it in a different colour if you fancy, something about more frequent collisions. Because that word frequent, that's something that you will need to explain to them in detail. It could say more often, more every second. As long as they're not just saying more collisions, they're saying more frequent collisions. That's giving their answer that precision that they really need. And what I quite often do at this point is say, well, okay, now let's consider the force, the push outwards because of these more frequent collisions. Is it going to be bigger or smaller? And they'll all be able to tell you that there must be a bigger push, which I'm going to label with my red arrows, and I'm going to show that this arrow downwards like this is going to be much bigger. Because there's more frequent collisions, the particle's going to be pushing out with a greater force. And really that's it. If there's a greater force outwards caused by those more frequent collisions, well, that means the pressure inside the inflated balloon is much bigger than the pressure inside the deflated balloon. And the structure of this lesson is then to get students writing about this. So once you've got students thinking about that and writing about it, you might want to show them another example. So the next one I'll do, and I'll just do this very briefly, would be temperature. So what I might do in this case is say, well, okay, we've considered what's going to happen if we add more particles into the balloon. Now let's consider what's going to happen if we have a balloon and we heat it. So the first thing I'm going to do is draw my balloon like this. So here's my balloon, and that's at room temperature, 20 degrees C or thereabouts. And I'm going to zoom in on the particles. And what I'm going to do this time is just show 10 particles. So I'm going to keep the number quite small. And I'm going to really draw their attention to that number because, as you might have guessed, that's going to be important later. So 6, 7, 8, 9, 10. And again, I'm going to show the particles moving in exactly the same way. But this time, I'm going to say, well, because it's at a low temperature, that means the average kinetic energy of the particles is quite low. So we've got another chance to build this concept of temperature being related to kinetic energy. So I'm going to draw some little arrows like this in different directions. Again, I'm going to try and scatter the movement of these particles so that there's an even number roughly bouncing off each wall. Maybe let's move that one over there to this wall. And then I'm going to show, well, okay, in this case, I've just got 2 particles every second or something bouncing off the walls. And actually, now I think about this, maybe you don't want to show all the particles bouncing off the walls, because you want to show later that when there's the higher temperature, you're going to get those more frequent collisions. But anyway, what I want to illustrate here is, because they're moving quite slowly, you don't get as many collisions every second. So what you've got is quite a small force here, like this. Now, quite often, as I think I said in the previous video, when I'm showing heating, I tend to just draw a candle or something like that. So let's imagine we heated this balloon with a candle, and we heated the air inside the balloon up to, let's say, 50 degrees C. So all I'm going to do now, I'll say, okay, I've heated this air up, so it's now hotter. I want to show that the balloon is roughly the same volume. Because these are not fixed walls, actually the air inside the balloon might expand, but we don't want to go into that for now because it's kind of year 7. A balloon is really fine as an example. I think it's a nice concrete example that they can visualize. All I'm going to do there is show what's going on in here. And again, this is where I would say, am I going to have fewer than 10 particles, more than 10 particles, or the same number, 10 particles inside? And lots of students might be encouraged or tempted, let's say, to say, I'm going to have more than 10 particles, because they've seen this example before of blowing up the balloon and they think, oh, well, there must be more particles now. What you need to emphasize is that there are not more particles. The number of particles is exactly the same. No particles have left the balloon or entered the balloon. So you want to emphasize that there's going to be the same number of particles. Just 10 in this case. So how many have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when you then come to question the students and really get them thinking, well, okay, what's going to be different about these particles? The idea you need to elicit is that these particles are going to be moving much faster, much faster, because the gas is now at a higher temperature. So I'm going to draw lots and lots of arrows like this. Now, maybe my diagram didn't show this very well. Actually, I should have had a few more particles pointing inwards to show that not as many are going to reach the sides of the balloons. It doesn't matter too much. I think students, once you've explained this and shown a diagram like this, they will get the idea that there's going to be more frequent collisions. So I might show those collisions going like this, as I've been doing before, because again, the really important idea that I want to stress in this lesson is that pressure in gases is all to do with the frequency of collisions. It's all about gas particles colliding with the walls. So I'm going to show those collisions, even though in my example it's got a bit messy. But the idea that I really want to get across is, because they're moving faster, they're zipping around all over the place really quickly, what you're going to have is more frequent collisions, and therefore you're going to have a bigger force. So what would you expect to happen if the particle model was true and you were to increase the temperature of the gas? Well, you would expect the pressure to increase. And that's where you might bring in the gas laws, either in this lesson or in a later lesson, and say, well, actually this is what happens if you measure pressure of a gas at different temperatures. You find that the pressure increases. Now, just one last note before I finish this video on getting students to write about this. Certainly when you get to GCSE, you are going to want your students to write something or answers to questions like this. So explain why increasing the temperature of a gas causes the pressure of a gas to increase. And I've done CPD elsewhere about overall cause and overall effect. But this is the kind of level that you can be coaching your students to write at. Now, depending on how much time you have in your curriculum, you may or may not want your year 7 or 8 students at Key Stage 3 to be writing like this, but it's worth emphasizing there's not really any reason why they shouldn't be able to do that. And if you give them a really clear picture of what's going on, and you give them lots of keywords, so particles, kinetic energy, time, frequency of collisions, walls, force, area, there isn't any reason why they shouldn't be able to answer that question in loads and loads of detail. You don't need to introduce the pressure equation. pressure equals force over area, because actually the key idea here is pressure is caused by collisions between the particles and the walls. You don't need to introduce any other equations like Boyle's law, because this is the qualitative introduction to the concept that underpins that more quantitative understanding later on. So I hope this video is useful. I haven't gone into how you would draw something to do with Boyle's law, how volume and pressure affect one another, but hopefully you can see the kind of structure that's going to be really helpful for scaffolding students' thinking around these examples. In the next lesson, we will look at pressure in liquids.